Section and ECS Respect webinar. Today is our honor to have Professor Katsuya Teshima from Shinshu University to give a talk on the Flux technology for regenerating lithium-ion battery materials. So thank you so much, Sensei, to give a talk to us today. So I would like to give the stage back to Sensei.
Thank you. Okay. Hi, good afternoon, everyone. I am Teshima from Shinshu University, Japan. I'm very honored to show my research here. Thank you very much, Sensei, Professor Taiz Sensei, and the organizer. In my talk, keywords are flux growth and flux coating method. This is our original and unique technology. So I'm explain shortly, briefly, Shinshu University flux crystal growth method, mainly battery materials, and innovative action flux coating method, and summary. Let me briefly explain about Shinshu University. Shinshu University is a comprehensive university with 9 faculties in 4 regions of Nagano Prefecture, like these pictures. Today is very, very cold in Nagano compared to Thailand. Uh, it's that's hot spring monkey is very, very famous. Next time, please come to Japan and Nagano. Shindai Crystal is engaged in a wide range of activities at Research Initiative for Super Materials, RISM. Recently, we make new faculties. There is Institute for Aqua Regeneration, located on the Nagano campus. RISM has 6 divisions and 1 laboratory. The research and development of Shindai crystals are conducted in the flux-grown crystal division. The 3 research areas of the flux-grown crystal division are crystal growth, material informatics, and sustainable materials-based biosources. Shindai Crystal is supported by these laboratory members. This is a member of 2024. This slide shows our laboratory experimental rooms of Shindai crystals. We have various kind of rooms. There is adsorption test, robotics room, photocatalytic test room, and battery test room. And we have 4 dry rooms. This slide shows the experimental facilities at Shindai Crystals. There is one example. We have a well-equipped research environment for synthesis and evaluation. Okay, now I'd like to introduce you to Shindai Crystal. Shindai crystal is a generic name for crystalline materials produced by the flux method and related technologies. These logos represent Shindai crystal, and one voice is solutions creating smiles, Shindai crystals. My research interests can be divided into four main categories. There is energetic materials, hydrogen produced materials, ion exchange materials, and functional materials. Today, I'll especially focus on energetic storage materials, that is, lithium-ion battery materials. So let me explain flux crystal growth. Do you know the flux growth? Flux growth is niche technique to make single crystals. Crystal growth is classified roughly into three. There is vapor phase, liquid phase, and solid phase. Liquid phase growth is divided into two. There is melt growth and solution growth. Flux growth is one of the solution growth. And flux growth is the most versatile method of growing crystals. For example, the components of the desired substances are dissolved in a water in a solvent, that is flux, and growth takes place at relatively low temperature. And a molten salt and a molten metals are used as the flux. These growth manners resemble those of minerals in the earth crust and its deep inner layers. So we call this technique nature mimetic method. For flux growth, choice of flux is very, very important because flux affect crystal growth considerably. It's necessary to meet many requirements to act as a flux. Flux should have low melting point, low viscosity, low toxicity, low reactivity, and so on. This figure shows typical two-component phase diagram. There is crystal and flux, crystal A and flux B. TA and TB are melting temperatures of crystal A and flux B. The most important thing is their eutectic temperature is much below than TA and TB. Flux growth is classified by the method of obtaining supersaturation into three groups. That is slow cooling method, evaporation method, and temperature gradient method. For temperature change, there is blue arrows. The supersaturation is usually achieved by cooling the solution. In the case of solvent extraction, that is red arrow, the supersaturation is mainly achieved by evaporating flux. Flux growth is very simple and low technique. However, it has many advantages. The, the principal advantage of using a flux is that crystal growth occurs at a low temperature than that required for growth from the pure melt. In addition, the following materials can be grown by the flux method, that is, incongruently melting materials, phase transition materials, and high vapor pressure and volatile constituent materials. Furthermore, other important advantages are crystals can grow free from mechanical or thermal constraints into the solutions. And the grown crystals have well-developed facets, that is, isomorphic structures. Okay, let's move the experimental section. For flux flows, its apparatus are very simple, only two, that is, energy source and container. We usually use various crucibles, platinum, aluminum, carbon, and so on. In addition, flux growth conditions are environmentally friendly. This is the experimental procedure, simply three steps: mixing, heating, and cooling. First, raw material such as solute and flux powders are mixed in air. Next, the mixed powders are put into crucibles, and then the crucibles are placed in an electronic furnace and heated at a given temperature for several hours. Finally, they are allowed to cool to room temperature, and the residual flux is dissolved in warm water to separate the grown crystals. Now, I'll show some example. These are the flux grown ruby crystals. Ruby crystal is made of aluminum and chromium. As clearly shown in these pictures, the grown crystals have isomorphic feature, that is hexagonal by pyramidal structure. In this case, the growth temperature is about 1000 degrees C. So it is about half of its melting temperature. Alumina uh, melting point of aluminum material is about 50 degrees C. So it's about half of its melting temperature. Here we present photocatalytic crystals that produce hydrogen. These are uh, various kind of visible light or ultraviolet light responsive photocatalytic crystals produced by Flux method, oxide, nitride, oxynitride, and so on. They are uniquely formed crystalline materials. These crystals are oxynitride crystals for water splitting. They have very unique structures, and we can make various kind of composition of photocatalytic crystals. These crystals are oxysulfide crystals for water splitting. They exhibit unique crystal shapes, and they also good water splitting performances. Now we are trying to make very wide photocatalytic panels to make hydrogen. One example is BTON, BATAO2N crystals. The BATAO2N crystals, an example of a visible light responsive photocatalyst, can split water to produce hydrogen and oxygen. As shown in this figure, we have also achieved the world's highest performance in water splitting. In 2021, we are currently implementing a project to produce large amounts of hydrogen using water splitting panels, just like solar panels. From here, I'll introduce the water purification crystalline materials. First, heavy metal ion adsorbent materials. In our laboratory, we have developed sodium titanate crystals that selectively adsorb heavy metal ions. The use of these crystals have made it possible to easily remove harmful heavy metal ions dissolved in water. The mechanism of ion adsorption is ion exchange uh, system. Now we have succeeded in mass producing these crystals and even commercialize them. This figure shows the water purification performances of Shindai crystals in ultra soft and high hard water conditions. Shindai crystals removes only heavy metal ions and therefore exhibit ultra high performances under high hardness conditions. This is a very important feature of Shindai crystals. So now portable water purification bottles containing Shindai crystal NTO are available. In addition, ultra simple water purification packs in the form of tea bags, as shown in this photo, are also available on the market. In addition, products incorporating Shindai Crystal NTO continue to expand throughout Japan. For example, they are incorporated into under sink and spouting water purifier cartridges, which are widely used in people's daily lives in Japan. As part of our SDGs activities to eliminate PET bottles, we are developing AquaSpot 3. 3 is Shinshu water for ecology and the environment. This is an initiative to encourage people to drink tap water in Japan, which has been installed at more than uh, 40 locations in Nagano Prefecture 2024, and it's still expanding. Next, I'll introduce a crystal materials that remove fluoride ions. In fact, fluoride ions are a big problem in the world. Now I'll back our big vision. We are currently working on water purification in Tanzania and Kenya, Africa. For example, our demonstration field is at the Mount of Meru and Mount of Kilimanjaro. Fluoride ions in water are major problems in many African countries like these pictures. For example, in the village of Lemanda, Tanzania, where the Maasai people live, uh, the fluoride ion concentration exceeded 15 ppm. This is more than 10 times the WHO standard of 1.5 ppm. Our laboratory has developed LDH crystals that absorb and remove fluoride ions. Because of its accordion-like shape, it can absorb fluoride ions with high efficiency. continue to fluoride overdose caused significant health problems in children. This picture shows a young girl with curved bones in her feet due to osteoporosis. These photos show the visit to the village of Lemandr, Tanzania, in 2020. We evaluated water at the water pumping area. These are pictures of the children from my visit in January of 2023. We saw many health problems caused by excess fluoride ions. This slide shows pictures from our visit to the village of Lemanda in January 2023. We installed our purification plant upstream of the water pumping area. This is the first water supply in this area. This slide shows a Shindai crystal NTO that removes heavy metal ions used in a water purification plant. It can remove heavy metal ions for more than 10 years without maintenance. This ensures that the water is safe and free of lead, cadmium, and other heavy metal ions. This is the Sendai crystal LDH that removes fluoride ions, which was used in a feasibility study at the water purification plant. Okay, let's move to today's main topics, battery materials. These pictures are active materials and solid electrolytes used in lithium-ion batteries. You can see that these crystals have beautiful shapes. We have started to sell these crystalline reagents as Shindai crystal LIB. Let me briefly introduce solid electrolyte for lithium-ion battery. These pictures show solid electrolyte grown by our Flux method. They have very beautiful crystal features, structures with well-developed facets. LLNO, LLZO, LATO, and LLZNO. This slide shows STEM HRDF images. A very clean atomic arrangement was observed in these pictures. The atomic arrangement drawn by the DFT calculations agreed well with the STEM images, like this slide. Next are active materials for leaves. This is a recipe of LiCoO2 LCO crystal growth. This LCO is the most basic LIB cathode materials. These are the starting materials, heating conditions, and crystal separation conditions. The grown crystals were analyzed by SEM, TEM, XRD, ICP-OES, and so on. These are the LCO crystals grown from NaCl flux. Idiomorphic uh, homogeneous LCO crystals were grown by the NaCl flux. The crystals have had hexagonal barrel-like shapes with well-developed facets. Uh, the median size was about 1.4 micrometer. These are the high-resolution TEM images. These images show the flux-grown crystals are LCO, and well-developed facets, well-ordered lattice, and sharp SAED spots, selected area electron diffraction spots, are the evidence of high-quality crystals. This is the charge-discharge performance of the flux-grown LCO crystals. The flux-grown crystals are relatively high quality, so their potentials can be drawn out to the maximum, and they show high performances as functional materials. As a result, the flux-grown crystals show good charge-discharge performances that is almost same as the theoretical value of LCO cathode. A key feature of flux-grown LCO crystals is that lithium ions can move at high speed. This makes it possible to charge the battery in a short period of time. These are various kinds of flux-grown LCO crystals, that is, hexagonal barrel, hexagonal nanoplate, hexagonal microplate, and ultra-long wires and millimeter order. We can control their shapes and sizes by using flux growth technique. This is one example of charge-discharge performances. This picture shows the ultra-long LCO wires, whiskers. They are very distinctive shapes as shown in this picture. The lithium ion move extremely fast compared to commercially arrived particles, commercially available particles. As can be seen from these same images, the LCO crystals are surrounded by 001, 012, 104, and 101 planes, faces. And the LMO crystals have well-developed structures surrounded by 111 faces. These are cathode LIB materials. As flux-grown crystals have well-developed facets, this is a clear evidence of high-quality crystals. So now these crystalline materials are available on market. Flux-grown crystals exhibit characteristic cycling properties due to the well-developed crystal facets. The, degradation mechanism is quite different from that of commercial particles, like these pictures. Upper is commercial LCO, down is flux-grown LCO. We have fabricated a variety of substitutional cathode materials to improve LIB performances. These pictures show titanium-doped LCO materials. The addition of titanium allows uniform particles to be grown. Crystal particles of different sizes can also be produced by controlling the crystal growth conditions, like these pictures. Fluorine substitution can improve loading performances. From these pictures, it can be seen that the performance can be greatly improved. It was found that the co-substitution of fluorine and copper result in even better performances, like these pictures, like these figures. This slide shows a two-particle mix system electrode. It was found that mixing the two types of particles could significantly increase the density and produce excellent battery performances. So let me briefly introduce an example of cathode materials for sodium-ion batteries, SiB. In recent years, sodium-ion batteries, NIB, have been attracting attention as an alternative to lithium-ion batteries. Like lithium-ion batteries, uh, sodium-ion batteries have an energy density of about 500 watt-hour per kilogram. Compared to leaves, uh, sodium-ion batteries have a slightly lower operating potential of about 3 volt, but they have the advantage of being low cost because they use sodium, which is abundant on Earth. Whereas positive electrode active materials are known for NIBs, such as Prussian blue type, polyanion type, and layered metal oxide type, and a wide variety of batteries characteristics have been reported. As a representative example of active materials, we focused on P2 type sodium cobaltate and ternary systems. These have a composition in which sodium ions between layers are missing, but sodium ion diffusion is easily, and they are characterized by multi-stage phase transition during electrochemical reactions. The battery characteristic of these materials include a long life based on multi-stage platters and excellent rate characteristic compared to O3 type. Such P2 type extend compound tend to glow in a high aspect ratio, usually in a plate shape based on a two-dimensional crystal structure. However, in this case, uh, there is an issue of the diffusions, long diffusion distance of sodium ions. Therefore, we thought that if we could reduce the aspect ratio of the crystals, they could be used as a high output active material. Flux was used to create low aspect ratio crystals. Usually, uh, experiments done by humans require mixing, heating, crystal isolation, and phase identification, which takes time. Therefore, this time we attempted high throughput experiments by introducing a robot into part of the processes. Specifically, we automated the mixing process and crystal isolation phase identification preparation. A video of the robot in operation is shown below. In addition, in addition, in addition, we increase the analysis efficiency by adding a 48 series outsampling function to the XRD measurement. As a result, the experiment speed was improved by about 10 times compared to manual labor. Furthermore, by incorporating data-driven experimental planning method such as the optionality criteria and Bayesian optimization, we further improve the experimental efficiency by more than 6 times. As a result, we succeeded in developing low aspect ratio crystals in about 3 months of actual works per compound. Sorry. As a result, for sodium cobaltate, uh, barrel-shaped low aspect ratio crystals were uniformly obtained, as shown here. The XRD pattern also confirmed that the P2 phase was obtained. Furthermore, TEM measurements shows that the crystals were single crystals or primary particle crystals with uniform orientation. Furthermore, the crystal stacking direction was consistent with stacking direction of the two-dimension layers, indicating that this shape is favorable for the diffusion of sodium ions. These are the identification results for NCM235 crystals, and it has been confirmed that similar low aspect ratio crystals were obtained. As for ternary systems, we have been working on growing 3 types of crystals: NCM154, 335, and 114. All have P2 type crystals, and we have succeeded in achieving low aspect ratio for NCM154 and 235. We are currently expanding the scope of crystal control to other layers oxide systems. We are currently building an extra, extraportion an extrapolation mechanical machine learning model. And we expect that we will be able to freely control the crystals of many layered oxide in the near future. Now I'm explaining our innovative action. In my previous slide, I showed Ruby crystals can be grown by our Flux method. By the way, these are very beautiful ruby and sapphire crucibles. In our lab, in my innovative story, when ruby crystals were grown in aluminum crucible, uh, the inside walls of aluminum crucible could be covered with very beautiful ruby crystal layers. This is the tip of our original flux coating. These are the cross-sectional same images of ruby crystal layers on an aluminum surface. As you can see, high-quality ruby crystals were directly grown on the aluminum surfaces. So, the individual ruby crystals hardly separate from the aluminum surfaces. These are the NIOX nano-whisker CNT composites. Under proper growth condition, CNTs couldn't decompose in the relatively high temperature flux. As a result, the surfaces of CNTs were completely covered with the flux-grown metal oxide crystals, like these pictures. As, as clearly shown in this picture, the obtained nanocomposite uh, have very unique structures. These are the PT nanoparticles CNT nanocomposite. In the special flux, simultaneously with the CNT nanobrush structure formation, PT nanoparticles were directly grown on the nanobrush surfaces like these pictures. They have very, very unique structures. These are the usual flux technique using typical crucible and our generation flux coating processes. Upper is general, downer is flux coating processes. This is an image of flux coating for ribs. Now we are planning to make roll-to-roll system for our flux coating method. Our coating process is highly expected in various industrial fields. Now we are trying to this system all solid state type lithium-ion batteries. Let's move to a new concept that is direct fabrication of crystal layers. These pictures show the LCO crystal layers on PT substrate, platinum substrate. The unique LCO crystal layers were successfully fabricated on PT substrates. The LCO layers consist of the dense LCO layer and the high-ordered plated LCO crystals. In addition, from the SAED image, the fabricated layer was single phase with R3 bar M. These are the LIB performances of LCO crystal layers. The LCO crystal layers exhibit charge-discharge performances. This is a large-scale LCO crystal layers on aluminum substrates. The layer was founded to be a single-phase LCO. And as you can see, the layer consisted of numerous platy LCO crystals. Now I'm checking these LIB performances. Here I'm showing plasma jet techniques as our new energy source. We call this technique plasma assisted flux coating method. This is a real-time movie. This substrate is completely covered with a flux ink, that is solute and flux. As the previous slide, electric furnace and hot plate are usually used as an energetic source. In our new proposal, this plasma jet is used as an effective energy source. This plasma jet have very high energy, so the heating time can be drastically decreased as compared to usual heating. Hmm? Oh, oh. Next is our new concept materials, that is densely packed cathode materials. These are the same images of LNMO crystal layers on platinum substrate. As clearly shown in these pictures, densely packed LNMO crystal layers were successfully fabricated on platinum substrate. The ground layer consists of numerous well-developed LNMO crystals. Single crystalline LNMO grew directly on the platinum surfaces. And the basic shape of the individual LNMO crystals is a spinel type structure. These are the 10 images of LNMO crystal layers on PT platinum substrate. As you can see, highly ordered LNMO crystals were directly grown on the PT substrate. No lattice defect was observed in the lattice image. These are the flux coating LNMO layers, uh, left side, and the commercial LNMO layers, right side. As you can see, the surface structure of the flux coating LNMO layer was quite different from that of the commercial layer, that is densely packed and highly ordered. The packing density of the flux grown layers over 99%. And the active material is about 1.5 times compared to a commercial cathode electrode. These are very important to improve LIB performances. These are the LIB performances of the densely packed LNM crystal layers. The flux-grown LNM crystal layer indicate typical LNM curves, almost the same as that of the commercial one. So the most important thing is no additives is used in the electrode. And it has very good cycle performances. Its coulombic efficiency is about 95%. That is much higher than that of a commercial one. And no capacity depression is shown in the cycle performances, like these figures. For our flux coating method, we can make various designed crystal layers. These are the CO metal electroplating line and space patterns and LCO crystal lines. First, CO cobalt metal line and space patterns are fabricated by electroplating and photolithography. In this case, these patterns act as a solute. After that, the pattern is uh, converted by the flux method. A very unique crystal structure can be fabricated using our advanced flux coating processes. These are the dot matrices, LCO patterns, as well as line and space patterns. We can make dot matrices by controlling the cobalt metal electroplating conditions. These are very unique flower-like dots. Let me briefly introduce a new concept, glass electrolyte flux. This is a new concept in glass electrolyte flux method. By using this technique, well-connected interfaces and void-free cathode layers can be fabricated. So smooth lithium-ion transfer can be expected in the new concept. In this glass electrolyte flux method, active material crystals glow in the molten glass. As a result, an interface is formed between the automatically bonded active material and the solid electrolyte. As clearly shown these pictures, unique LCO LBSO composite was fabricated by our novel glass flux method. LBSO is glass solid electrolyte. LCO crystals have had hexagonal plate-like shapes with well-developed facets. And LCO crystals were completely covered with glass electrolyte LBSO matrices, like these TEM images. This slide shows the EDS analysis of the hybrid materials. The interface is found to be very clear, like this EDS mapping. These are the crystal structure and TEM images of LTO crystal anode materials. This is one of the anode material. As well as cathode materials, densely packed LTO crystal layers were fabricated by our flux coating method. As you can see, highly crystalline LTO glue directly on the surface. And the basic shape of the individual LTO crystal is spinel type structure, like these TEM images. These are the lattice image of LTO crystal layer on PT surfaces. The LTO crystal layer have very beautiful lattice, like these pictures. No defect and no byproducts are observed in these lattice images. These pictures show the flux-grown LTO LBSO composite. The individual LTO crystals were clearly covered with the LBSO glass fluxes, and their interface are very beautiful in the high-resolution TEM images. As well as the LCO composite, the LTO LSBO interface was very clear, like this EDS mapping. Recently, we have fabricated unique materials. In these materials, the active material is covered by a very uniform solid electrolyte thin film. We call this zero grain boundary conductive glass. Sorry, We call this zero grain boundary conduction glass electrolyte. As shown in these figures, XRD, SEM, TEM, and EDS, they are very well combined. Let me briefly introduction example of material recycled for lips. That is the main topics. Background identification of phenomena using positive electrode material deterioration and experimental result condition consideration and challenges. I'm sorry, I'll skip this slide. Okay, I'll shortly, briefly explaining. In 2030, the lithium-ion batteries will contain 12% CO, 4% lithium, and 4% nickel recycled materials, lead flame. Uh, However, the challenges of lithium LIB recycling have been reported in news. The LIB recycling business doesn't create high industrial opportunities. There are two main combinational methods for general regeneration of LIB materials. Recently, flux evaporation method was proposed as a promising method for lithium-ion battery regeneration. The LIB particles NCM523 was used to determine the cause of deterioration. 1000 cycle charging and discharging test was carried out. After 1000 cycles, several cracks occurred, like yellow arrows. It has been previously reported that cracks are generated in the positive electrode used for a long period of time. After 1000 cycles, chemical structure deterioration occurred, like these figures, XRD patterns. After 1000 cycles, lithium dropped by 35%, and other materials remained. Number one and three recycling cracks replenizing lithium can be realized by the flux evaporation method. Lithium source, flux material, and deteriorated particles were added as raw materials to produce crystal particles. Crystal particles could be synthesized from secondary particles. Lithium was replenished for crystals particles. Replenishing Li by the flux evaporation method and solid phase method were carried out based on the references. XRD measurements were compared. Flux evaporation method showed good cation mixing performances. Battery performances of secondary particles, deteriorated secondary particles, and regeneration crystal particles were compared. The regeneration crystal particles can reproduce the battery performances of the NCM523. Compared to other method, the flux evaporation method reconstructs deteriorated particles into crystal particles, which can achieve the regeneration requirements, like these tables. When we recover the deteriorated particles, aluminum foil is also recovered together. when the flux evaporation method is implemented in an aluminum foil containing state, the battery capacity decreases significantly. Aluminum foils made from substrate. Along with aluminum foil separation technology, it's hoped that flux evaporation method will become a lithium-ion battery recycling method. Finally, I'll show some hot topics, which is phase diagram and the grain boundaries. Here we change the subject. We have recently succeeded in producing phase diagram based on DFT calculations. This diagram, this diagram can also represent crystal facets. This figure relates to grain boundaries. Recently, we are calculating some tilt angle grain boundaries by use of first principle calculation. In this case, it was found that metastable crystalline facet join provide superior lithium-ion conductivity. In other words, boundaries of thermodynamically stable crystalline surfaces is detrimental to lithium-ion conductivity. Okay, I'm conclude my talk. Today, I'll explain various kinds of crystals and crystal layers fabricated by flux concept. In our flux techniques, these are various possibilities of next generation energy and environmental materials, such as lipids and so on. Since the crystal is beginning to expand globally, we will challenge ourselves to solve various environmental and energy problems in the future. We hope to create a world full of smiling faces with Shindai crystals. Okay, thank you for your kind attention. I'm sorry to extend my talk.
Okay, thank you very much, Sensei, for the very informative talks on the frog grow crystals. Okay, so right now the forum is open for question. So if you have question, please feel free to type in the chat. Sensei, there is a first question in the chat. So did you need any heat treatment after the flux growth state when synthesizing solid electrolytes like LLZO or LLTO?
In this case, we didn't use post annealing, so we don't need any heat treatment.
Oh, no heat treatment.
Yeah, no heat
Nice.
treatment. Yeah.
Okay. Actually, I also have some question. Sensei, when you glow the crystal on, like when you use in the battery, and then you said that you use flux coating.
Mhm.
So in that case, you don't need to have any carbon particle on the electrode at all, right? So it's only metal and then connect with the LCO or like those oxide directly.
Yeah. In this case, we are only use metal substrate, but now we are trying to make various carbon hybrid materials. So in our case, we can use carbon materials for substrate, electrode materials.
Oh, so you plan to use like
Yeah,
carbon
yeah, yeah, yeah.
substrate and then glow the oxide on top of the carbon substrate.
Yeah, yeah. If you need
Ah.
carbon substrate, please send me carbon materials for
I see. So
electrode.
in that case, there is no problem of electronic conduction, like for the oxide to the. I
Perhaps,
mean, the reason that they mix carbon is for to improve the electronic conductivity, right? But I just wonder, like, so for your case, you didn't observe any problem on that.
maybe yes. Today I'll show some image of nickel oxide carbon nanotube hybrid materials. So uh, by
Mm-hmm.
using our flux coating techniques, we can make
I
cathode and
see.
another materials, carbon hybrid materials. Maybe we will make,
So it's
we can
also
make, yeah,
possible as well.
yeah, I think so.
A very powerful technique for the
Thank you.
fabrication. Any other question? Feel free to type in the chat. I have another quick question on the for when you try to regenerate the lithium.
Mhm.
Use like from the lithium-ion battery. The one you mean you said the 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 part that you said like aluminum foil
Yeah.
like recycle, you mean you just take the whole part of
Mhm.
the electrode out
Mhm.
together with the substrate and then reclone it on the like on that electrode directly,
Mhm.
so you don't need to take off the oxide for the recycle, right? So you can directly clone on top of the
Yeah.
substrate.
Yeah, that's very important issue. Important.
uh,
I am trying to directly convert it. Now, our collaborator is completely separate from activated materials from electrodes. So we are
right.
now using these materials. But next step,
uh,
we want to use directly materials that is used electrode materials. We don't have used electrolyte material. I don't have used electrode material. Do you have used electrode materials? We can't
no,
get to. We couldn't get to. So if we get to use the electrode materials, we can try to make a directly conversion.
that's will be interesting because you can reduce the like the process, right, of
Yeah. I think so. I think so.
separation, like uh, disassemble, right, all the like
Yeah,
substrate
yeah,
and
yeah.
the powder
That's
out.
right. That's right.
Mhm.
Now our collaborator cannot supply used electrode materials, only used particles. So we are trying to recover used particles. Uh, Near
I
future,
see.
we want to try directly convert it.
Oh, that will be very interesting. Thank you, Sensei. Any other question from the audience? When you mentioned about the crystal, and then you mentioned about the high performance of the flux clone crystal such as LCO
Mhm.
compared to the commercial
Mhm.
particle.
Mhm.
I just wonder the reason that it has higher performance is it because of it has some certain orientation of the crystal that match with the preferred diffusion path of the lithium, or is it because of you have lower amount of the grain boundary, or I just wonder like what is the main reason that your fractal crystal has much better performance
Yeah.
compared with the commercial?
Yeah. And in the case of flux grown crystals, uh, very nice, good lithium-ion passes in their bodies. So lithium-ion is very
Uh,
fast, move to very fast. So
uh,
they showed very high performances compared to commercials powders. So
oh,
they
okay,
have
because
very
you can
nice.
choose the preferred
Yeah.
orientation, like
Yeah.
where it's mainly have the preferred direction of the lithium movement,
Yeah, I think so.
something like that.
And crystal facet is very important. 001 facet,
Uh,
plate facet is not good for lithium ion moving. But in our case, we can control their facets.
uh,
104 and 110 is very important to lithium ion batteries, lithium moving. So in our case, we can make various unique barrel type LC powders. Barrel type is very nice performance. Show very
mhm.
nice, very nice performances. because they have nice, good lithium-ion passes on their surfaces. So
I see.
104 and 110 is very, very important passes.
I see. So it turned out that the surface migration also very important factor
Yeah, I
for
think
the
so.
for
Yeah.
performance. There is one more question in the chat. Is each grown particle shown in the images a single crystal
Yeah, I think, yeah, that,
in each
yeah,
particle?
yes.
I see. So you relatively have, we also relatively have large grain as well, right? So
Yeah.
not much of the grain boundary for the blocking
Yeah, I think so.
process. Oh, let's see. Okay, so I think we all have learned a lot from Sensei Sensei Dr. Titi also thank you in the chat.
Thank you very much.
Okay, so I believe everyone learned a lot about the potential of this growth techniques, and thank you so much, Sensei, for sharing with us.
Yeah,
So
and
I think it's already the time that. So thank you so much, Sensei. It's very informative talks, and we have learned like the very nice potential, nice application of these techniques.
thank you very much. And I'm look forward to meeting you soon.
Okay, seeing you soon.
Yeah, see you
Yeah.
in Shinshu. And Shinshu is very, very cold, so please take care.
Oh, I will be prepared for that.
Yeah.
Okay, thank you so much, Sensei, and thank
Okay,
you
thank
all the
you.
audience for joining us today.
Yeah, thanks so
Okay, so
much.
I will close the session right now. Thank you.
Thank you very much.
Okay, bye,
Bye.
Sensei.